Unit 7, the P block elements. Objectives of this unit: after studying this unit, you will be able to appreciate general strengths in chemistry of elements and groups 15, 16, 17 and 18. Learn the preparation, properties and uses of dinitrogen and phosphorus and some of their important compounds. Describe the preparation, properties and uses of dioxygen and ozone and chemistry of some simple oxides. Know allotropic forms of sulfur, chemistry of its important compounds and the structures of its oxoacids. Describe the preparation, properties and uses of chlorine and hydrochloric acid. Know the chemistry of interhalogens and structures of oxoacids and halogens. Enumerate the uses of noble gases. Appreciate the importance of those elements and their compounds in our day-to-day life. This is the periodic table, and the P block elements or the groups which we are going to study about is the nitrogen 15th, oxygen 16th, fluorine 17th and the noble gases 18th groups. The 15th group has elements of nitrogen, phosphorus, arsenic, antimony, bismuth and moscovium. The next group, which is the 16th group, has oxygen, sulfur, selenium, tellurium, polonium, livermorium. And the 17th group has fluorine, chlorine, bromine, iodine, astatine, tennessine. And the noble gases of the 18th group are helium, neon, argon, krypton, xenon, radon and oganesson. We are not going to go into the higher elements and mostly on the upper elements. I'll tell the groups again. The 15th group, nitrogen, phosphorus, arsenic, antimony, bismuth. 16th, oxygen, sulfur, selenium, tellurium, polonium, livermorium. 17th, fluorine, chlorine, bromine, iodine, astatine, tennessine. The 18th group, helium, neon, argon, krypton, xenon, radon and oganesson. Now let's continue. Diversity in chemistry is the hallmark of P block element, manifested in their ability to react with elements of S, D and F block element as well as their own. The P block elements can react with all S, D, F and even P block elements themselves. This is their ability. In class 11, you have learned that the P block elements are placed in groups 13 to 18 of the periodic table. From boron carbon as well. The boron group containing boron aluminium, gallium, indium, thallium, and nihonium. It is not completely non-metals. It has metalloids and metals. Their valence shell electronic configuration is Ns2, N1, N1 to 6. General configuration is Ns2, N1 to 6 of p block elements. Except helium, which has 1s2 configuration. Even though helium has a 1s2 configuration, it is a noble gas and is placed in the 18th group. The properties of p block elements, like that of others, are greatly influenced by atomic sizes, ionization enthalpy, electron gain enthalpy, and of course electronegativity. As for what these are, atomic sizes is defined as the size of the atom. Ionization enthalpy, the energy required to remove an electron from the outermost shell or the valence shell from an atom of an atom. Electron gain enthalpy, the energy released or needed to add an electron to the outermost shell. And electronegativity, the ability of the atoms to attract the electron density. The absence of d orbitals in the second period and the presence of d or d and f orbitals in heavier elements starting from third period onwards have significant effect on the properties of elements. In periodic table, if we see, helium has a 1s2 configuration. Helium has a 1s2 configuration. Neon has 1s2 and 1s2, 2p6, 1s2, 2s2 and 2p6 configuration, and goes on with the below elements even having d and f orbitals in their atoms. In addition, the presence of all three types of elements, metals, metalloids and non-metals, bring diversification in chemistry of these elements. There are metals, metalloids and non-metals in the p block element. Having learned the chemistry of elements of group 13-14 of the p block periodic table in class 11, you will learn the chemistry of the elements of subsequent groups in this unit, which is 15th, 16th and 17th and 18th. Starting with group 15 elements. Group 15 elements being nitrogen, phosphorus, arsenic, antimony, bismuth and moscovium. Group 15 includes nitrogen, phosphorus, arsenic, antimony and bismuth. They did not consider moscovium here. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. Here in the 15th group, nitrogen is a non-metal, phosphorus is a non-metal, arsenic and antimony are metalloids, whereas bismuth is completely metal. These are the 15th group elements. As we go from the first period to the sixth period, the metallic character increases, or the metalloidic character increases, as these both are metalloids. These both being non-metals, and bismuth being a metal. Group 15 includes nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. Nitrogen and phosphorus are non-metals, arsenic and antimony are metalloids, and bismuth is a typical metal. Occurrence. The first topic is occurrence. Okay, let me write again. General configuration except helium is NS2 NP126, and the first topic is 15th group elements. 15th group elements consist of nitrogen, phosphorus, arsenic, antimony, and bismuth. Non-metals, metalloids, metal. First to last period, metallic character, non-metallic character to metallic through metalloids. This is what was given, and the beginning of the first topic being occurrence or finding of these metals. Of the, not metals, but of these elements of the 15th group, let's see. Occurrence: molecular nitrogen comprises 98% by volume of the atmosphere. In the earth crust, it occurs as sodium nitrate NaNO3, called child saltpeter, and potassium nitrate Indian saltpeter. It is found in the form of proteins in plants and animals. Phosphorus occurs in, and first let me write the occurrence of nitrogen. Nitrogen comprises molecular nitrogen, which is N2, comprises 78% of atmosphere, for atmosphere by volume. Second, found as child saltpeter, sodium nitrate, and Indian saltpeter, KNO3, in the earth crust. And the third, found in living organisms as protein, as proteins are made of amino acids, and amino acids contain nitrogen. The next is phosphorus. Phosphorus occurs in minerals of the apatite family. Apatite family, I guess it is salts of calcium phosphate. Yes, apatite family being salts of calcium phosphate. This is phosphorus occurs in minerals of the apatite family. Ca9PO46 dot CaX2. X can be any halogen or OH group. Example for apatite Ca9PO46 CaF2, which are the main components of phosphate rocks. Phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as living cells, as living cells are made of living cells contain nucleic acid or DNA. DNA is made of phosphate, or basically nucleotides. Nucleotides contain a pentose sugar, a nitrogen base, and a phosphate group. Phosphoproteins are present in milk and eggs. Arsenic, antimony, and bismuth are found mainly as sulfide minerals. So basically, in sort of minerals, it is found as a mineral of the apatite family, calcium salt family, and which constitute the phosphate rocks. And phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as living cells. And as for arsenic, antimony, and bismuth, they are found as sulfide minerals. One found in apatite family, where apatite family, I will write the definition later, which constitute phosphate rocks, and the apatite family is a family of calcium phosphate calcium salts, calcium phosphate salt. Example, fluoroapatite, and second, found in living cells. And they gave that it is present in the bones and found as phosphoproteins, which can be seen in eggs and milk. And as for arsenic, antimony and bismuth, these are found in the earth crust as sulfide ores or sulfide forms. Or sulfide minerals, actually, not sulfide forms but sulfide minerals. The important atomic and physical properties of this group elements along with their electronic configuration are given in table 7.1. Atomic and physical properties of group 15 elements. Atomic number of nitrogen is 7, atomic mass is 14, electronic configuration is 2s2 2p3, ionic, and this is with a half-filled p configuration. Ionization enthalpy for the first one is the 1400, which is the highest in the group. This is because 2p3 is a stable configuration and it is a small atom. And the second is also the highest in all the group, with the third one also being relatively very high compared to the other elements. And the order is, for the first enthalpy, it is nitrogen followed by phosphorus, arsenic, antimony and bismuth. So order is decreasing as we go through the group. Ionization enthalpy decreases through the group. This is a basic trend, and this is followed by the p block elements, at least in case of the first enthalpy. And as for second enthalpy, this is somewhat true, but in case of bismuth, the second enthalpy seems to be a bit higher than antimony, but we can still consider it to be in trend. And as for the third ionization enthalpy, here as well antimony is slightly exceeded by bismuth, but we can still follow the trend that for 15th group elements, first ionization enthalpy N greater than P greater than arsenic greater than antimony greater than bismuth. Second ionization enthalpy N greater than P greater than arsenic greater than bismuth greater than Sp. Very slight difference. Third ionization enthalpy Np arsenic, and here as well antimony is the least. So we can say the 15th group elements follow the basic trend of decrease in ionization enthalpy along the group, or we can say down the group. Follow the basic trend of decrease in ionization enthalpy along the group. This is the case for ionization enthalpy. And let's see electronegativity. With nitrogen having the highest electronegativity, followed by phosphorus, arsenic, antimony and bismuth. This also follows the general trend as electronegativity keeps decreasing as we go down the group. So electronegativity of 15th group elements this also follows the trend. Electronegativity decreases as we go down the group, is followed by these elements with electronegativity order being N greater than P greater than arsenic greater than, actually the antimony and bismuth have same, which we saw in the NCERT. There will be slight differences, but we can indeed say it is 1.9, 1.9. As for the covalent radius, with N having the least and bismuth having the highest, this is normal because covalent radius is influenced by the size of the atoms. If higher the size, higher the bond length. Because N is a small atom having the least number of shells, as we see here, whereas bismuth having 5d, 6s and even 6p shells, subshells, or the 6 being the highest shell. As N number increases, actually there is, I believe, not need, it is a general property. As the size increases, the size of the atomic radius increases, the bond length or covalent radius also increases. Because of such a reason, bismuth has the highest and nitrogen has the least. Ionic radius, with nitrogen having the highest ionic radius and P212 and antimony having the lowest, followed by bismuth. What is difference between ionic radius and covalent radius? I know that covalent radius is bond length. Then what about ionic radius? Antimony have the least ionic radius. The ionic radius is the effective distance from the nucleus of an ion to the outermost shell of electrons. It represents the size of an ion in a crystal lattice or when it forms a compound. Key points: cations, positive ions are smaller than their neutral atoms. They lose electron, reducing electron-electron repulsion and pulling remaining electrons close to each other. Anions are larger than their neutral atoms. They gain electrons, increasing repulsion and expanding the electron cloud. 215 nitrogen family. More electron shells are added, shielding increases, effective nuclear charge on the electron weakens. But we saw that the atomic radius here antimony has the least ionic radius. I did not get why antimony has the least, but basically ionic radius is the size of an ion in a compound or a crystal. When in an atom loses electrons, due to less electron repulsion and the decrease in shielding effect, the size decreases. And for anion, it is the opposite. As more electrons are added, more the electron repulsion, more the size. So, okay, let's leave anionic radius melting point with arsenic having the highest melting point in Kelvin and nitrogen having the least. As nitrogen is a gas, it does indeed have the lowest melting point. And arsenic has the highest melting point. Arsenic followed by antimony and bismuth, and that followed by phosphorus, and the least melting point is nitrogen, which is similar in boiling point as well, where the boiling point of nitrogen is 77 Kelvin and phosphorus it's 554 and arsenic it is 888. And here, as for the boiling point, it keeps increasing as we go down the group, and with antimony and bismuth having approximately same melting point, boiling point. The only difference is we see in the melting point, where arsenic has the highest melting point. The boiling point anomaly with arsenic followed by antimony followed by bismuth followed by phosphorus followed by nitrogen, and melting point which is not anomaly as nitrogen as antimony approximately equal to bismuth followed by arsenic followed by phosphorus followed by nitrogen. This is the trends for melting and boiling points. And as for density, of course, is a general trend with it increases as we go down the group, and it is because also the metallic character increasing. Because of this, the density of the bismuth being the highest and nitrogen being the least. Trends of some of the atomic, physical, and chemical properties of the groups are discussed below. And I didn't discuss these three: atomic mass and electronic configuration along with atomic number. The atomic number of nitrogen is 7, phosphorus is 15, arsenic is 33, antimony is 51, bismuth is 83. The masses are 30, 70, approximately 31, 75, 122 and 209. And the configurations, which always end at a half-filled configuration of 6p3, N p3 electrons. This is not an there is no exception here. All elements seem to have half-filled p configuration, and all the before shells or before subshells seem to be completely filled. Okay, now let's see the next topic, which is the electronic configuration of the 15th group elements. The valence shell electronic configuration of these elements is ns2np3. The s orbital in these electrons is completely filled and p orbitals are half filled, making their electronic configuration extra stable. The general configuration I gave before was for the p block elements. Now it is for the 15th group elements, which is basically always has half filled p subshell configuration which is ns2np3. All the orbitals or subshells before p subshell are completely filled. With electrons. This is the electronic configuration. Let's go to the next topic. Atomic and ionic radii. Covalent and ionic in a particular state, radii increase in size down the group. The general trend is as they increase down the group, there is a it seems the covalent radii is atomic radii. There is a considerable increase in covalent radius from N to P. However, from arsenic to bismuth, only a small increase in covalent radius is observed. This is due to the presence of completely filled d or f orbitals in heavier members. These d or f orbitals are very poor at shielding. So the effective nuclear charge on the outer electron increases, and thus if the effective nuclear charge is increasing, the nuclear charge will pull the electrons toward the center. This will thereby reduce the size of the atom. Okay, atomic radii. Yes, as this happens where we see the atomic radius, the covalent radius, there is a 40 picometer increase. Here there is only a 11 picometer increase as we go from phosphorus to arsenic, and there is a 20 increase in antimony to arsenic, and only a 7 increase from bismuth and antimony. This is covalent radius, and this is U2. As you see here, there is f orbital, f subshell and d subshell in the bismuth, and antimony has d orbitals. Even arsenic has d orbitals. And one more point in electronic configuration is that provides extra stability due to half-filled configuration. As for the ionic radius and covalent radius, it seems that they generally increases in size down the group as number of shells are added. This is due to presence of d and f orbitals. And the next topic being ionization enthalpy. Ionization enthalpy decreases down the group due to increase in atomic size because of the extra stable half-filled p orbitals, electronic configuration and smaller size. If there is high stability, the ionization enthalpy will always be very high. The ionization enthalpy of group 15 elements is much greater than that of group 14 elements in the corresponding periods. The order of successive ionization enthalpies as expected is H1 smaller than H2 smaller than H3. If we see, it is indeed the case where the first ionization enthalpy is 1400 and the second being 3000 and the third being 4500 or 600. This is as expected, and this seems to be followed in all cases, and the general trend of decreasing in the ionization enthalpy as we go down the group is followed here completely in case of the first ionization enthalpy, and somewhat disobeyed in the case of antimony and bismuth, with antimony having a slightly lower ionization enthalpy than bismuth. It is very minute, here being 15 and here being somewhat 23. As such, we can generally say that the 15 group elements follow the general trend of decrease in ionization enthalpy as we go down the group. Decreases down the group due to gradual increase in atomic size because of the extra stable half-filled configuration, p orbitals, electronic configuration and a smaller size. The ionization enthalpy of group 15 elements is much greater than that of group 14 elements in the corresponding periods. The order of successive ionization enthalpy as expected is as such. And a line to be remembered, the ionization enthalpy of 5th group elements is much greater than that of 14th group elements. This is because these elements have a half-filled p configuration which is very stable, and because of such a reason, when corresponding elements of the 14th group are taken, these group elements have a higher ionization enthalpy as we are ruining the stability here. Electronegativity. The electronegativity in value in general decreases down the group with increase in atomic size. However, amongst the heavier elements, the difference is not that much pronounced, as we saw here. Electronegativity with nitrogen having the highest, followed by phosphorus, arsenic, antimony, and bismuth, with only being a zero point 0.1 change, with where from nitrogen to phosphorus there was a 0.9 change, but from arsenic 0.1, antimony 0.1 change, and bismuth being even less of a change. This general trend is somewhat followed, but there is not much difference. Physical properties. All the elements of this group are polyatomic, meaning they can't be like single. It can be said that it will bond with two or more atoms and cannot remain single. Dinitrogen is a diatomic gas, dinitrogen being N2 gas, while all others are solid. Metallic character increases down the group. Basically, he is saying that I still have a doubt, so SB2 and possible, and if so, are they solids? I'm not sure if bismuth and antimony are possible. It seems that they don't exist. I guess they are talking about not the diatomic gases but polyatomic substances, which mostly are solid. I have a doubt. All elements of this group are polyatomic, dinitrogen, while all others are solid. What does this statement mean? All elements of this group are polyatomic. Dinitrogen is a diatomic gas, while all others are solid. All the elements of this group are polyatomic. This means in their elemental form, meaning they don't exist as isolated single atoms such as noble gases. They bond with themselves to form molecules or extended structures. Polyatomic here doesn't strictly mean discrete molecules with multiple atoms. It includes networks, solids, or metallic lattices formed from many atoms of the element. Dinitrogen is a diatomic gas. This is unique among group 15. nitrogen N2 exists as a stable diatomic gas with a strong triple bond. It is colorless, and odorless gas at room temperature. The triple bond gives it exceptional stability and makes it very unreactive under normal conditions. While all others are solid, they do not form simple diatomic molecules in nature. Instead, they exist as P4 molecules: white phosphorus, polymeric or layered solids, red black phosphorus, arsenic antimony, metallic lattice. These forms are all solids at room temperature due to large atomic size, weaker bonding in small molecules, and increasing metallic character. So basically, they are saying these exist as solid and only nitrogen exists as a gas. Or nitrogen is the only element able to form gaseous compounds at room temperature. Fine. It seems, let's just read. All elements of these groups are polyatomic. Nitrogen is a diatomic gas while all others are solid. Metallic character increases down the group because we see a shift from non-metal to metalloid and metal, so metallic character of course increases down the group. Nitrogen and phosphorus are non-metals, arsenic and antimony metalloids, and bismuth is a metal. This is due to decrease in ionization enthalpy and increase in atomic size. As electropositivity increases, ionization also increases. Ionization enthalpy decreases. The boiling point as electropositivity, meaning the ability to become a cation or to easily give electrons. In such a case, the ionization enthalpy should be less. In general, increase from top to bottom in the group. But melting point increases up to arsenic, then decreases up to bismuth. Except nitrogen, all elements show allotropy. Allotropy meaning having different structures. For example, carbon can exist in different structures of diamond, graphite, and fullerene, where diamond is a 3D structure where carbon has 4 bonds, where graphite is a sheets like structure where numerous sheets are arranged, and fullerene is a football like structure. And except nitrogen, all the elements show allotropy. This is except nitrogen. Wait, I should write the before physical properties about physical property I will not write all the points, but note point is N nitrogen, actually except nitrogen, all other elements of this group show allotropy. This is a physical property. Chemical properties, oxidation states and trends in chemical reactivity. Common oxidation states of these elements are -3, +3 and +5. This is because when we see the valency, it is np3, so the 3 electrons can be donated. This enables them to show a +3, or they can gain 3 electrons to have a completely filled p orbital, completely filled p subshell. In such a case also stability is acquired, so they show a +3 and -3, and they can also show +5 state because there is a ns2 electrons, 2 electrons in the s subshell. These can also be donated. These act as a lone pair of electrons. When we see ammonia, there are one lone pair. Because of this, the ammonia molecule has a pyramidal shape, whereas a tetrahedral geometry. These lone pairs are from this NS group. Now they show -3, +3 and +5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in metallic character. This is obvious because the anionic property is generally not shown by metals. As we go down the group, electropositivity increases. Because of such a reason, the electropositivity and the metallic character increases. Because of such a reason, -3 oxidation state is not shown very much, and it is shown based on this trend. We see that this is shown more in nitrogen. In fact, the last member of the group, bismuth, hardly forms any compound in -3 oxidation state. The stability of +5 oxidation state decreases down the group. The only well characterized B5 plus compound is BiF5. The stability of +5 oxidation state decreases, and that of +3 state increases due to inert pair effect down the group. Nitrogen exhibits +2 +1 +2 +4 oxidation state also when it reacts with oxygen. Phosphorus also shows +4 +1 oxidation state in some oxoacids. Basically, they show three kinds of oxidation state, which is +3, -3 and +5. As we go down the group, -3 is decreased and +5 decreases as we go down the group as well, as heavier elements are not stable in high oxidation states. This is reverse for metals or transition elements, where the higher or heavier metals or heavier atoms show or tend to show higher oxidation state, which is reverse of what is here, which say that like higher atoms prefer lower oxidation states, because +5 is a higher oxidation state and +3 is a lower oxidation state. Bismuth would rather prefer +3 oxidation state than +5, and they gave the only well characterized compound in the +5 state of bismuth is BiF5, bismuth pentafluoride, and they said this is due to inert pair effect, inert pair being the electrons, the inert pair electrons, I believe. Yes, you are. What is inert pair effect? Inert pair effect is the tendency of outermost s electrons in heavier p block elements, especially in group 13 to 16, to remain non-bonding inert, resulting in lower oxidation state than expected. The inert pair refers to two s electrons in the valence shell. These electrons are less likely to participate in bonding as you go down the group, so they remain a lone pair, making the atom favor a low oxidation state. So in bismuth, for example, +5 state, valence electron is 6s2 and 6p3, total of 5 valence electron. This +5 is not possible. This is 6s2 not participating. Why does the inert pair effect happen? Poor shielding by d and f block electrons. Okay, because of the shielding effect of the poor shielding effect, the bad shielding effect of d and f block, d and f subshells or electrons in them, which is what we call as lanthanoid or actinoid contraction, which decreases the size of atom. Therefore, the nuclear charge increases, attraction increases, and the s block elements are harder to remove, causes outer s electrons to feel a stronger pull from the nucleus. Relativistic effects in heavy atoms, the s electrons get contracted and stabilized, making them less available for bonding. These d and f block elements, d and f block, f not elements but d and f orbitals, can only be seen in as we go down the group, meaning heavier atoms. So as we go down the group, due to the inert pair effect, the s electrons do not participate in bonding for a lower oxidation state. Energy cost is too high. Okay, thank you. So, oxidation state. common oxidation states are +3, -3 and +5. A -3 state is less common as we go down the group, as or because electropositivity increases down the group. Electropositivity increases down the group. Because of that, this negative oxidation state is not really seen. And as for +5, due to inert pair effect, also is less common as we go down the group. All in all, +3 is more preferred. And one of the example is only characteristic or characterized +5 oxidation state in bismuth is BiF5. As for what is the inert pair effect, in p block elements, the ns 2 electrons do not tend to participate in bonding for heavier atoms, or in other words, as we go down the group, this is because of high attraction on ns2 electrons due to poor shielding of D and F subshells. Okay, this is basically the inert pair effect, and basically plus 3 is common, minus 3 decreases as we don't go down the group, plus 5 also decreases as we go down the group, and for individual elements it will start. Nitrogen oxidation states. Nitrogen exhibits plus 2 plus 1 plus 2 and plus 4 oxidation state when it reacts with oxygen. In the case of nitrogen, all oxidation states from plus 1 to plus 4 tend to disproportionate into acid solution. For example, HNO2 will give HNO3 plus H2O plus 2NO2, 2NO. This is HNO2 3 times 1 plus X plus 2 minus 2 equals 0. So 3 plus minus 4 equals 0, and X equals 4 minus 3. Here the oxidation state is 1 for nitrogen. In HNO3 it is plus 5, and NO it is plus 2. So this is a acid solution. All oxidation states, it may be plus 1 plus 2 plus 3 and plus 4, they will disproportionate, meaning undergo disproportionation reaction, meaning one of the compound, like here in case here HNO2, the nitrogen has a plus 1 oxidation number, and here HNO, in case of HNO3 it has plus 5, meaning nitrogen got oxidized. But in case of NO, if we see, both got oxidized. Right, yes. It is not 3, it is 1 hydrogen. 1 plus H minus 4, it will be 4 minus 1, so it will be 3. From 3 oxidation state to it got disproportionated reaction to HNO3 with plus 5, which got nitrogen, in this case got oxidized to give nitric acid, and then NO, which is plus 2, meaning nitrogen there got reduced. This is what we call disproportionation reaction. Both reduction and oxidation happens for the same compound or same element. This we can say that it is tending to be more stable in case of plus 5. Similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into +5 and -3 both in alkali and acid. So all intermediate oxidation state, we saw that in case of phosphorus shows +1 and +4 oxidation state in some oxoacids here. And when phosphorus, all oxidation states formed by phosphorus generally disproportionate into +5 and -3 both in alkali and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth becomes increasingly stable with respect to disproportionation. Basically, +3 is not stable in case of most of the cases. In case of generally in case of nitrogen phosphorus, where nitrogen any stage between +1, +2, +3 and +4, nitrogen tends to disproportionate to give an acid, a nitric acid solution or an acid solution, where in case of phosphate or phosphorus groups, not phosphate, phosphorus groups, all intermediate oxidation states, any oxidation state except +5 and -3, all these states will disproportionate into +5 and -3. This happens in both alkali and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth becomes increasingly stable with respect to disproportionation. So nitrogen is restricted to maximum covalency of 4 since only 4 orbitals of 1s and 3p orbitals are available for bonding. The heavier elements have vacant d orbitals in the outermost shell which can be used for bonding covalency and hence expand their covalence, as in pF6. Okay, so the oxidation states of nitrogen can have states +1, +2 and +4 reacting with oxygen mostly all intermediate all states of +1 to +4 will disproportionate to give an acidic solution, acid solution. oxidation states. So nitrogen oxidation states, mostly it will show +1, +2, +4 oxidation states reacting with oxygen, and mostly all states between +1, +2, +3 and +4, all these will disproportionate to give an acid solution, which is HNO2. Here it is +3 will disproportionate to, example, HNO2 will disproportionate to give HNO3, nitric acid, plus H2O plus NO2. No, wait, it is NO. Here nitrogen's oxidation state is +5, whereas here it is +2. Here it's getting reduced as oxidation number decreases, whereas here it is getting oxidized. This is what we call a disproportionation redox reaction. And this is the case for nitrogen. In case of phosphorus oxidation states, it will also show +1 and +4 in some oxacids, meaning reacting with oxygen, but mostly all oxidation states, most common oxidation states is +5 and -3. Mostly all other states will disproportionate to give +5 and -3 state in both alkali, meaning base, and acidic mediums. And phosphorus valency is not limited to 5. It can actually form elements like PF6 by expanding their valency. Phosphorus, nearly all intermediate oxidation states disproportionate into +5 and -3 in both alkali and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth becomes increasingly stable with respect to disproportionation. I believe it means it is +3 is very stable. Nitrogen is restricted to maximum of 4 valency, since only 4 s orbitals, for a 1s orbital and 3 p orbitals. Total of 4 orbitals are available, but heavier elements have vacant d orbitals in outermost shell, which can use for bonding and hence expand their covalency or valence. This is and the next is for bismuth, arsenic, bismuth and antimony. These elements, they show the most common oxidation state of +3, as it is increasingly stable with respect to disproportionation. Normally, node point only nitrogen has a final valence of 4 orbitals, this is fine. Covalence of 4 orbitals, because there are only 4 orbitals for bonding. Remaining heavier atoms have vacant d orbitals or other orbitals which can participate in bonding to increase the valence, or we can say instead of 2, thus or thereby increasing the covalence. Example which they gave is PCl, no, it is PF6 minus, yes. This is the oxidation states about the 15th group elements. Now the next main topic being anomalous properties of nitrogen. Nitrogen differs from the rest of the members of this group due to its small size, because it is in the second group, whereas second period, high electronegativity. It has the highest electronegativity. I believe it's in the Pauling scale. It is 3. High ionization enthalpy and non-availability of d orbitals. No d orbitals, and as we saw, the ionization enthalpy in all three ionizations was nitrogen was having the highest. Nitrogen has a unique ability to form p pi like p orbital pi multiple bonds with itself and with other having small size and high electronegativity. I think they are talking about where here one is the sigma bond, two are pi bonds. Basically, this is due to small size, high ionization enthalpy, high electronegativity, that is basically the characters, right? And of course, lack of d orbitals. Due to which we see nitrogen being able to form a max of 2 p orbital pi bonds, with condition being 1, they should be small in size. Second, highly electronegative. Atoms. For example, we can take carbon and oxygen, because these are they are small atoms, because carbon's atomic number is 6, oxygen it is 8, therefore they are small in size and they are relatively electronegative. The first property is pi bonds with small highly electronegative atoms or elements. C and O, heavier elements of their group do not form pi bonds, as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Heavier elements of this group do not form pi bonds, this is p orbital bonds, as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Thus, we see this is possible. Thus, nitrogen exists as a diatomic molecule with a triple bond. 1s and 2 pi, 1 sigma and 2 pi. As for the reason they gave, that as to why heavier atoms let's try note in different color. Note larger, or in other words heavier atoms slash elements of the 15th group cannot form multiple pi bonds because their orbitals are very large and hard, and it is hard to overlap. Covalent bonds are formed by overlapping, so overlapping is hard, so this is also hard. And one more, they said something about diffusing. They also diffuse easily or something like that. Seems highlighted if I use the pencil, so okay. Then the next, between two atoms, consequently its bond enthalpy is 941.4 kilojoule per mole, is very high. If the as the enthalpy, bond enthalpy is the energy required to break bond, and bond enthalpy is directly proportional to the bond order being the number of bonds. If higher the number of bonds, higher the bond enthalpy. Because of such a reason, when nitrogen forms 3 bonds, the bond enthalpy is also very high because bond order is very high, meaning 3. On the contrary, phosphorus, arsenic and antimony form single bonds as P single bond P, arsenic, and SbSb, while bismuth forms metallic bond in elemental state. However, the single NN bond is weaker than the single PP bond because of the high inter-electronic repulsion of the non-bonding electrons. Owing to small bond length. As a result, a NN triple bond is stronger than any other bonds, but NN single bond is pretty much weaker than the other compounds bonds. This is why, because high inter-electronic repulsion of the non-bonding electrons. N will have, if it makes a NN single bond, it will have 4 extra electrons which are not bonded but which are in the valence shell. And because the nitrogen atom is a small atom, it is also a small bond length. Because of that only the electrons will repel. As a result, the catenation tendency is weaker in nitrogen. Catenation tendency. Catenation is the ability of atoms or elements to form long chains. If the NN bond is itself like weaker, the catenation, this property of making large branches or large chains is also reduced. In carbon, we see huge chains of heptane, octane, or decane, etc. are formed. There are other complex organic compounds, which is one of the main reason. Catenation of carbon is one of the main reason we are reading organic chemistry, or we have such an complex organic chemistry. And because of this small bond length, the catenation tendency, the forming of branches, is weaker in nitrogen. Another factor which affects the chemistry in nitrogen is the absence of d orbitals in its valence shell. So here they explain that the triple bond is very strong. The first anomalous property of first here let's continue. N triple bond N has a very high bond enthalpy because bond enthalpy proportional to bond order. But N bond is much weaker than any phosphorus bond or other bonds, other single bond. This is due to one, intraatomic electron repulsion of non-bonding electrons small size and bond length of nitrogen mostly due to electron repulsion. If small size, then more electron repulsion. And this this inability for nitrogen to opt to make, basically I am saying nitrogen can indeed make n single bonds, but it's just that it can't opt or like prefer these bonds. Reduces nitrogen's catenation tendency. Where catenation is the property of atoms or elements to make branches, not branches but long chains of compounds bonding to itself and other elements. This is catenation. That is what they are saying, the catenation tendency is weaker in nitrogen. How many pages? 3 pages. Okay. Another factor which affects the chemistry of nitrogen is the absence of d orbitals in its valence shell. Besides restricting, oh yes, this is the second anomalous factor. Second anomaly, lack of d orbital. Besides restricting its covalency to 4, nitrogen cannot form d pi and p pi bonds as the heavier element can. Example, R3, R is an ER group, P is phosphorus, it's a double bond with O, or R3P, double bond CH2, or R is an alkyl group. Phosphorus and arsenic can form d pi and d pi bonds as well. Also with transition metals, when their compounds like and acting as ligands. Ligand meaning donors of electron. Okay. Lack of ability to form d pi and p pi bonds, basically overlap between d and p orbitals. and overlap between d and d orbitals. Unlike phosphorus and arsenic, which phosphorus and arsenic can even act as ligands because of having d orbitals. But this option is restricted to nitrogen because it doesn't have d orbitals. Its valency is also reduced to 4 or restricted to 4. Okay. I think we are starting with chemical properties next. Chemical properties. Reactivity towards hydrogen. All the elements of group 15 form hydrides of type EH3, where E is any N, P, A, S or SB, or basically the 15th group elements. Is there any name for the 15th group? Okay, let's call it the nitrogen group itself. And there is also pnictogens. We can call them pnictogens as well. It even gave a meaning of what nigine meaning choke or okay. Let's call it pnictogens or nitrogen group, where E is a part of pnictogens. Some of the properties of these hydrides are shown in table 7.2. Ammonia, pH3, ASH3, SPH3 and BiH3. Melting point with ammonia having the highest melting point, then antimony, SBH3 followed by ASH3 and PH3. Boiling point, it is ammonia followed by ammonia, and wait, the highest is antimony. No, it is bismuth hydride. Bismuth having the highest hydride. First ammonia has the highest, then it goes on increasing in the ascending order. Ammonia increase, then from phosphorus it goes in the normal ascending order. For boiling and melting points, with bismuth hydride they did not mention the melting point. Distance of the pnictogen and the hydride bond is, for NH3 it is 101 and for pH3 it's 141. Basically as we go from As we go down the group, the distance increases, where PM is picometer. This is the bond angle. I believe this angle, this is 107.8 degrees in case of NH3, where the structure is tetrahedral, but it is 93 or in the 90s for pH3, for phosphorus, arsenic and antimony. As for this is delta formation enthalpy. Formation enthalpy is negative for ammonia, and it increases as we go down the group, with bismuth having the highest. And dissociation enthalpy, with ammonia having the highest dissociation enthalpy, which decreases as we go down the group. Okay. Reactivity towards hydrogen. All the elements of group 15 form hydrides of type EH3. Chemical properties. First one is reactivity towards hydrogen. All the nitrogens form EH3 type of bonds with hydrogen. The hydrides show regular gradation in their properties. The stability of hydrides decreases from NH3 to BiH3. Which can be observed from their bond dissociation enthalpy. Bond dissociation enthalpy, NH3 has the highest bond dissociation enthalpy, and as we go down it decreases. Consequently, the reducing character of hydrides increases. Reducing character meaning ammonia is only a mild reducing agent, while BiH3 is the strongest reducing agents among all the hydrides. A reducing agent meaning the power to get oxidized. Reducing agent meaning it will give electrons. NH3 is a mild reducing agent, while BiH3 is the strongest reducing agent. Basicity also decreases in the order NH3, PH3, arsenic and antimony, followed by bismuth. Basicity meaning the power to release electrons. Basicity donates an electron pair. Bases donate an electron pair, according to Lewis theory. NH3 having the highest basicity, but I think it is in case of accepting proton as well, because we saw that it is a mild NH3 is a mild reducing agent, which means it can't easily give electrons. If that was the case, BiH3 should be the highest basic, but that is not the case, where NH3 is the most basic. But so that must be in case of taking H plus. So basically NH3 can take H plus H plus to give NH4 plus ammonium ion. Maybe that is the reason it is ammonia having highest basicity. So basically there are 3 points in the reactivity towards hydrogen, where the nitrogens will form EH3 compounds with hydrides, and the first point, the stability of this hydride decreases from ammonia to bismuth, and which can be observed from the bond dissociation enthalpy. And the reducing character also of the hydrides increases, with ammonia only being a mild reducing agent, while bismuth is a strong reducing agent. Basicity decreases in the order from up to down. 3 points highlighting the basic structure of EH3, the stability, the reducing character, and the basicity. 4 points. Okay. Reaction with hydrogen. So all nitrogens will react with H in EH3 or as EH3, where E equals N P arsenic, antimony, and bismuth. And as for the second point, stability, NH3 is the most stable. Stability decreases as we go down, with bismuth hydride being least stable. And the third point, as we can observe in dissociation enthalpies. Third point is basicity of NH3 is highest can easily accept NH3 plus H plus to become NH4 plus. Basicity of BiH3 is lowest. Yes, this is the order. As for the fourth point, it's about reducing power. NH3 is a mild reducing agent, whereas BiH3, bismuth hydride, strongest reducing agent of all hydrides. This is the point. This also reducing power increases down the group. Okay. Now it will be reactions with oxygen, which I will be writing in pink color. In the next page. Reactions with oxygen all these elements from two types of oxides of E2O3 and E2O5, where the oxidation states are in E2O3 oxidation number of E equals it is +3, whereas in E2O5 it is +5. Yes. The oxides in the higher oxidation state of the element is more acidic than that of lower oxidation state. Their acidic character decreases down the group. The oxide in higher oxidation state of the element is more acidic than that of lower oxidation state. Their acidic character decreases down the group. This happens because higher oxidation states are not common in heavier elements. This is in P block element. I will write a note. Note P block elements tend to prefer lower oxidation states as we go down the group, meaning heavier atoms prefer lower oxidation state. And this is exactly reverse and transition element, where the heavier atoms tends to prefer higher oxidation states. Transition meaning D block elements, that we'll see in D and F block chapter. So as higher oxides, here in this case of E2O5 the oxidation state is 5 and E2O3 oxidation state is 3. Based on this definition we can say that E2O5 is more acidic than E2O3. But as we go down the group, this is not preferred. This oxidation state is not preferred, whereas the low oxidation state 3 is preferred. Because of that, as we go down the group, these oxides will be more and these oxides are less acidic, so acidity decreases as we go down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. It is N2O3 or P2O3 are purely acidic. That of arsenic and antimony are amphoteric, meaning they can react with both bases and acids to give salt and water, meaning they can undergo neutralization reaction both through acids and bases. And those of bismuth predominantly basic. Metalloids, we see non-metals form acidic compounds, whereas metalloids of antimony and arsenic form amphoteric oxides. We can say, yes, we can say oxides, amphoteric oxides, whereas the bismuth, which is a metal, forms basic oxide, which is basically normal. Non-metals form acidic oxides, metalloids form amphoteric oxides, whereas metals mostly form basic oxides. This is a reactivity towards reactions of oxygen. I will write it. reactions with oxygen mainly two compounds of E2O3, E oxidation state, oxidation number equals 3, and E2O5, yes, E2O5, or E oxidation number is 5 plus 5. And basically they are saying that the higher the oxidation number, the higher the acidity, as lower oxidation number or state is preferred. I wrote it wrong. As we go down the group, acidity of the oxides decreases down the group. And as for the next point, it is about nitrogen phosphorus purely acidic oxides form purely acidic oxides, arsenic and antimony form amphoteric oxides, whereas bismuth forms predominant basic oxide. This is the, I believe, reactions with oxygen. Okay, that is reactivity towards oxygen. The next will be reactivity towards halogens. Okay. Reactivity towards halogens. These elements react to form two series of halides, which is EX3 and EX5. Nitrogen does not form pentahalide due to non-availability of the d orbitals in its valence shell. Even though these are the main two series, in case here we saw that due to the d orbital's presence, phosphorus can even form PF6. F is a halide, so PF6 is also possible. here these two types, nitrogen doesn't form EX5 due to non-availability of d orbitals in its valence shell. Pentahalides are more covalent than trihalides. Okay, all the trihalides of these elements except of those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except bismuth fluoride are predominantly covalent in nature. They are basically saying bismuth fluoride, trifluoride is ionic in nature. So the points is they form two series of halides, which is EX3 and EX5. Nitrogen does not form. Okay, these two series are trihalides and pentahalides. Nitrogen doesn't form pentahalides due to non-availability of d orbitals in its valence shell, and they are saying that pentahalides are more covalent than trihalides. All the trihalides of these elements except those of nitrogen are stable. Basically, nitrogen trihalides except nitrogen trifluoride is stable, except nitrogen trifluoride are not stable. Trihalides except bismuth trifluoride are covalent in nature. Bismuth trifluoride is ionic in nature. Okay. Became a star, but this is better. Reactions with halogens. Can form trihalides, pentahalides. But nitrogen cannot form pentahalides EX5 due to lack of d orbitals. Except NF3, all other trihalides of nitrogen are unstable all trihalides except bismuth trifluoride are mostly covalent in nature. These are the reactions with halogens. And the fourth is reactivity towards metals All these elements react with metals to form their binary compounds exhibiting -3 oxidation state, such as Ca3N2 calcium nitride, Ca3P2 calcium phosphide, Na3As2 sodium arsenide, zinc antimonide, and magnesium bismuthide. So the metals reactivity, they gave a few examples. Mostly form binary compounds, meaning only these two kinds of element will form compounds to exhibit -3 oxidation states. Example: Ca2N2, Ca3N2, Ca3P2, Na3As2, Zn3sp2, Mg3Bi2. These all exhibit a -3 oxidation state. This is the reaction with the metal. Then the next topic will be preparation. Though nitrogen, let's see the example. Though nitrogen exhibits +5 oxidation state, it does not form pentahalide. Give reason. Nitrogen with N2, they did not give a reason. They just, in the textbook, they did not give a reason, and they just gave that nitrogen doesn't form stable it does not form pentahalides. Now let's see a reason in the solution, or for this example. Nitrogen with N equals 2 has s and p orbitals only. It does not have d orbitals to expand its. Okay, yes, they actually gave a reason. Yes, N being the principal quantum number, meaning it's the shell number, which is 2, which is 2s to 2p3. Because of that, it can only have 4 valency or 4 covalence. That is why it does not form a pentahalide. Basically, lack of d orbital. That is why it does not form pentahalide. pH3 has lower boiling point than NH3. Why? Unlike NH3, pH3 molecules are not associated through hydrogen bonding in liquid state. This is why the boiling point of pH3 is much lower than NH3. hydrogen bonding in like if this is a NH3 molecule and this is another NH3 molecule, there will be intramolecular hydrogen bonding because nitrogen is a highly electronegative element. This hydrogen bonding will increase the boiling point. Okay, then why are pentahalides more covalent than trihalides? If I remember correctly, then they gave that trihalides except bismuth fluoride are predominantly covalent in nature. Then they are asking pentahalides more pentahalides are more covalent than trihalides. Why is BiHCl strongest reducing agent among the hydrides of group 50? Reducing agent meaning it should be strongly oxidizable. It should have a strong oxidizing capacity, so it will undergo strong oxidation. Bismuth, being a metal, is very electropositive, can undergo oxidation very easily. Maybe that is the reason bismuth hydride is the strongest reducing agent. As for why pentahalides are more covalent than trihalides, I'm not too sure. Why pentahalides are more covalent than trihalides? According to Fajan's rule, a compound is more covalent if a cation is small and highly charged, high polarizing power, the anion is large and easily polarizable. Okay, there's high overlap between orbitals, favoring covalent bonding. +3 and +5. +5 is higher charge, so more covalent. Reasons pentahalides are more covalent: in higher oxidation state, greater polarizing power, high positive charge on P, pulse electron density from chlorine atoms, increased polarization, more covalent character. More polarization of halides electron cloud. Okay, electron sharing versus electron transfer. Pentahalides lean more toward electron sharing, not because of bond count but because of the nature of the electron cloud distortion. Basically following Fajan's rule, which says that smaller cation which is highly charged, meaning high polarizing power, and anion should also be large and easily polarizable. In case of pentahalides, the oxidation number on the nitrogen it will be plus 5. So it will have a high, the cation will be small and it will be highly charged. Okay. Let's see this question. Yes, it can easily release hydrogen. One more way of oxidation. Oxidation is not only loss of electrons and reduction is not only gain of electrons. Oxidation we can define as the addition or addition of oxygen or removal of hydrogen. Reduction we can define as addition of hydrogen and removal of oxygen. In such a case, with bismuth hydride, where BiH bond is the weakest, we can easily oxidize it by removing the hydrogen. A reducing agent donates electrons or releases hydrogen. In hydrides, reducing ability is ability to how easily molecule can give up hydrogen. So ammonia can't easily give up the hydrogen, so it is weakest, and this is why it's very stable. And pH3, it is a weaker bond strength, it's less stable. And arsenic hydride, it is unstable. Antimony hydride it decomposes easily. And bismuth hydride, it's extremely unstable. Stability decreases, reducing power. Okay, why is it's because it can easily be oxidized. Okay, with this I will be ending the stream. Good night.